In this lesson, we will present Hilbert's axioms of congruence. So we have already looked at Hilbert's axioms of incidence and betweenness. In this video, we're going to discuss his axioms of congruence, and then later we'll talk about continuity and parallelism. So as a quick reminder, here are the incidence axioms. So I'm just going to list them, not read them out. And then the betweenness axioms that we studied in the last lecture. So recall that our last undefined term is the word congruent. So we've already talked about point and line and between, and now we're going to talk about congruent. So we use the word congruent to describe objects that have the same size and shape. And really we have two ways to use congruent. So far we have congruent line segments and we have congruent angles. So in a moment we'll talk about a third use of the word congruent to be congruent triangles. But we also recall that we had common notions with the word congruent. So these are Euclid's common notions that a thing is congruent to itself and that things congruent to the same thing are also congruent to each other. So now let's talk about congruent triangles. We say that two triangles are congruent if a one-to-one correspondence can be set up between their vertices so that the corresponding sides are congruent and the corresponding angles are congruent. And if you recall back to high school geometry class, that CP/CTC phrase, corresponding parts of congruent triangles are congruent, that's what we mean. So congruent triangles have the same shape and size, and there's a one-to-one correspondence between their vertices and sides. Now, when we write that, for example, triangle ABC is congruent to triangle DEF, we understand that the order of the letters defines that correspondence between the vertices. So A corresponds to D, B to E, and C to F, and then that determines the corresponding sides. So now let's look at congruence axiom 1. If A and B are distinct points, then if A prime is any point, then for each ray R emanating from A prime, there exists a unique point B prime on R such that B prime does not equal A prime and segment AB is congruent to segment A prime B prime. So this axiom says that you can move segment AB so that it lies on ray R with A superimposed on A prime and B superimposed on B prime. Congruence axiom 2 states that if AB is congruent to CD and AB is congruent to EF, then segment CD must be congruent to segment EF. Moreover, every segment is congruent to itself. So this axiom replaces one of Euclid's common notions because it says that segments congruent to the same segment are congruent to each other. And it also replaces another common notion that says that segments that coincide are congruent. So segments are congruent to itself. Congruence axiom 3. If B is between A and C, and B prime is between A prime and C prime, and segment AB is congruent to segment A prime B prime, and segment BC is congruent to segment B prime C prime, then segment AC is congruent to segment A prime C prime. This axiom also replaces a common notion since it says that if congruent segments are added to congruent segments, the sums are congruent. Here we mean adding to mean juxtaposing segments along the same line. Congruence axiom 4 states that given any angle BAC and given any ray A prime B prime emanating from a point A prime, then there is a unique ray A prime C prime on a given side of line A prime B prime such that angle B prime A prime C prime is congruent to the angle BAC. This axiom can be paraphrased to state that a given angle can be laid off on a given side of a given ray in a unique way. Next, congruence axiom 5. If angle A is congruent to angle B and angle A is congruent to angle C, then angle B is congruent to angle C. Moreover, every angle is congruent to itself. So this axiom is the analog for angles of congruence axiom 2 for segments. So it would seem natural to assume that the next axiom would be an addition axiom for congruent angles, analogous to congruence axiom 3 for addition of congruent segments. But we don't need to do this because we can actually prove that result using the next and final congruence axiom. So congruence axiom 6, which is also known as the side angle side criterion for congruent triangles. This states that if two sides and the included angle of one triangle are congruent respectively to two sides and the included angle of another triangle, then the two triangles are congruent. So this is a famous criterion for showing that two triangles are congruent that you're familiar with from high school geometry. This side angle side criterion for congruence of triangles is a profound axiom which actually allows us to deduce all the other basic results about triangle congruence that you're probably familiar with from high school. This next result is corollary to the side angle side axiom. Given a triangle ABC and a segment DE that's congruent to segment AB, there's a unique point F on a given side of line DE such that triangle ABC is congruent to triangle DEF. So let's look at the following proof. By congruence axiom 4, there's a unique ray DF on a given side of line DE such that angle CAB is congruent to angle FDE. Then by congruence axiom 1, point F can be chosen to be the unique point such that segment AC is congruent to DF. And then we can use the side angle side criterion to conclude that triangle ABC is congruent to triangle DEF. This next result is another application of the side angle side axiom. It states that in triangle ABC, if segment AB is congruent to segment AC, then angle B is congruent to angle C. So this result says that if you have an isosceles triangle, then the base angles of the isosceles triangle are congruent. And the proof was actually done by Pappus in around the year 300 AD. So the proof goes like this. Well, we are given that segment AB is congruent to segment AC, and we know that segment AC is congruent to segment AB, and angle A is congruent to itself. So therefore, we have triangle ABC is congruent to triangle ACB by the side angle side axiom. So therefore, we can conclude that angle B is congruent to angle C because corresponding angles of congruent triangles are congruent. So it's very short and clever proof. Now let's begin looking at some familiar results on congruence. Some of these have proofs in the textbook, some of the proofs we'll examine together, and some of the proofs will be given as homework exercises. Proposition 3.11 states that if B is between A and C, and E is between D and F, then and segment AB is congruent to segment DE, and segment AC is congruent to segment DF, then segment BC is congruent to segment EF. The proof of this proposition is given in the homework section. It's a homework exercise to justify each step of the proof. So we can think of this as a segment subtraction proposition. Next, let's look at proposition 3.12. Given segment AC congruent to segment DF, then for any point B between A and C, there's a unique point E between D and F such that AB is congruent to DE. And we're going to present the proof of this proposition. By Congruence Axiom 1, there's a unique point E on ray DF such that AB is congruent to DE. So we need to prove that point E is between D and F. So if indeed E is between D and F, then we're done. So now let's suppose that E is not between point D and F. Then we either have two cases. Either E is equal to F, or F is between D and E by definition of ray DF. So let's look at the case when E equals F. If E equals F, then B and C are two distinct points on ray AC such that segment AC is congruent to DF, which is congruent to AB. So this is by hypothesis and by step 1. Well, this contradicts the uniqueness part of Congruence Axiom 1. So we see that E can't equal F. So to continue the proof, let's look at the other case when we assume that F is between D and E. So if F is between D and E, then on the ray opposite to ray AC, there's a point G such that FE is congruent to CG by Congruence Axiom 1. Then by Congruence Axiom 3, AG is congruent to DE. And since AB is congruent to DE, which we assumed in step 1, then we have that AG is congruent to AB by Congruence Axiom 2. Thus, there are two distinct points, B and G, on ray AC, such that AG is congruent to DE, which is congruent to AB. But again, this contradicts the uniqueness part of Congruence Axiom 1. So therefore, F cannot be between D and E, and therefore E is between D and F, and that finishes the proof of proposition 3.12. Before we prove some more propositions, let's look at the following definition. The notation segment AB less than segment CD means that there exists a point E between C and D such that AB is congruent to CE. The notation CD greater than AB means the same thing as AB is less than CD. This gives us a way to say that one segment is smaller than another segment without actually having to go through and defining what the length of a segment actually is. So this definition only depends on the undefined terms between and congruent. So now we can present some more propositions. Proposition 3.13 on segment ordering. The first part of proposition 3.13 states that exactly one of the following conditions holds. Segment AB is less than CD, AB is congruent to CD, or AB is greater than CD. So there's a trichotomy here, and only exactly one of the following conditions holds for any two segments, AB and CD. The second part states that if AB is less than CD and CD is congruent to EF, then segment AB is less than EF. Part C, if AB is greater than CD and CD is congruent to EF, then AB is greater than EF. And part D, if segment AB is less than segment CD and CD is less than EF, then AB is less than EF. So I'm going to present the proof of proposition 3.13 part A only. So we know that either segment AB is congruent to segment CD or they're not congruent. Well, if AB is congruent to CD, then we must show that neither of the other two cases can occur. So that is that we need to show that AB is not less than CD and that AB is not greater than CD. In the case when AB is not congruent to CD, we must show that either AB is less than CD or AB is greater than CD, but not both. So this will show that there's three states and exactly one of those statements can be true at the same time. So let's start by assuming that AB is congruent to CD. And then for a contradiction, let's start by assuming that AB is less than CD. Well, then there's a point E between C and D such that AB is congruent to CE by definition of less than. Then E and D are two distinct points on ray CD such that CE is congruent to AB and CD is congruent to AB. Well, this contradicts the uniqueness part of Congruence Axiom 1. So thus, we can conclude that AB is not less than CD. To continue, now let's assume still that AB is congruent to CD, and for a contradiction, let's assume that AB is greater than CD. The proof is pretty similar to what we just looked at. There exists a point E between A and B such that CD is congruent to AE. Well, then E and B are two distinct points on ray AB such that AE is congruent to CD and AB is congruent to CD, again contradicting the uniqueness part of Congruence Axiom 1. So thus AB is not greater than CD. So we see that if AB is congruent to CD, then the other two statements are not true. So we're finished with the case when AB is congruent to CD. So now for the rest of the proof, we're going to assume that AB is not congruent to CD. And now we need to show that either AB is less than CD or AB is greater than CD, but not both. Well, by Congruence Axiom 1, there exists a unique point F on ray CD such that AB is congruent to CF. Then this unique point F cannot equal D because we know that AB is not congruent to CD, but AB is congruent to CF. So we couldn't have F and D being the same point. So then we have two possibilities. F is between CD or D is between C and F. Well, if F is between C and D, then AB is less than CD by definition of less than. If D is between C and F, then by proposition 3.12 and the fact that AB is congruent to CF, there exists a unique point G between A and B such that AG is congruent to CD. Thus, AB is greater than CD by definition of greater than. Therefore, we have shown that exactly one of the following conditions holds. AB is less than CD, AB is congruent to CD, or AB is greater than CD. This definition of supplementary angles was given earlier this semester, so as a review, if two angles BAD and angle CAD have a common side, ray AD, and the other two sides, ray AB and ray AC, form opposite rays, then the angles are supplements of each other. or they're called supplementary angles. Now we can present proposition 3.14, which states that supplements of congruent angles are congruent. Let's also review the definition of vertical angles. Angle BAC and angle B'A'C' are vertical angles if A equals A prime, so that is that they have the same exact vertex, and ray AB is opposite ray AB prime, and ray AC is opposite ray AC prime. An angle BAD is a right angle if it has a supplementary angle to which it is congruent. So now let's look at proposition 3.15. Part A states that vertical angles are congruent to each other, and part B says an angle congruent to a right angle is a right angle. So let's look at some more propositions that are results of the congruence axioms. Proposition 3.16, for every line L and every point P, there exists a line through P perpendicular to L. Proposition 3.7, this is the angle-side angle criterion for congruent triangles. Given triangle ABC, a triangle DEF with angle A congruent to angle D, angle C congruent to angle F, and segment AC congruent to segment DF, then triangle ABC is congruent to triangle DEF. Proposition 3.18, which is the converse of proposition 3.10, if in triangle ABC we have angle B is congruent to angle C, then segment AB is congruent to segment AC, and therefore triangle ABC is isosceles. That is, it has at least two sides that are congruent. Proposition 3.19 is an angle addition result. Given ray BG between rays BA and BC, and ray EH between rays ED and EF, and given that angle CBG is congruent to angle FEH, and angle GBA is congruent to angle HED, then when we add these congruent angles together, we get that angle ABC is congruent to angle DEF. Next, proposition 3.20 is angle subtraction. So we have all the same assumptions except for angle ABC is congruent to angle DEF as proposition 3.19, and then we can conclude that angle GBA is congruent to angle HED. Now we have a definition of less than for angles, which corresponds to the use of less than for line segments. The notation angle ABC is less than angle DEF means that there's a ray, EG, between ED and EF such that angle ABC is congruent to angle GEF. The next proposition, proposition 3.21, is analogous to a previous proposition for ordering of segments. So this proposition describes ordering of angles. Part A states that exactly one of the following conditions holds given two angles, P and Q. Angle P is less than angle Q, angle P is congruent to angle Q, or angle Q is less than angle P. Part B, if angle P is less than angle Q and angle Q is congruent to angle R, then angle P is less than angle R. Part C, if angle P is greater than angle Q and angle Q is congruent to angle R, then angle P is greater than angle R. Part D, if angle P is less than angle Q is less than angle R, then angle P is less than angle R. Next, we'll present another criterion for showing that triangles are congruent, the side-side-side criterion. Proposition 3.22 states that given triangle ABC and triangle DEF, if segment AB is congruent to DE and segment BC is congruent to segment EF and AC is congruent to DF, then we can conclude that these two triangles, triangle ABC and DEF, are congruent. If you recall from geometry in high school, there's one more standard criterion for showing that triangles are congruent, the angle-angle-side criterion. This is presented in chapter 4. So we'll hold off for now on angle-angle-side criterion. The next proposition is proposition 3.23, which is Euclid's fourth postulate that states that all right angles are congruent to each other. So under Hilbert's axioms, it's no longer necessary to assume that all right angles are congruent to each other because we can prove this from Hilbert's axioms. So now we're going to look at the proof of this proposition. So we're going to start by assuming we have two right angles. And so we know that by definition, right angles have congruent supplementary angles. We need to show that these two right angles are congruent to each other. So given right angles BAD and FEH, we're going to assume that their congruent supplementary angles are angles CAD and GEH, respectively. And then we're going to assume to the contrary that angle BAD is not congruent to angle FEH. So here is a drawing of these right angles, and we're going to use these diagrams in our proof. So in step 2, then we know that one of the angles is smaller than the other, and so without loss of generality, let's just assume that right angle FEH is less than the right angle BAD. Then by definition of less than, we know that there is a ray, AJ, between rays AB and AD, such that angle FEH is congruent to angle BAJ. Then by proposition 3.14, which states that supplements of congruent angles are congruent, we can conclude that angle CAJ is congruent to angle GEH, because these two angles are supplements of the congruent angles in step 3. And for step 5, we can say that angle CAJ is congruent to angles FEH by steps 1 and 4 and by Congruence Axiom 5. This is because angle FEH is congruent to angle GEH. Now, since angle FEH is less than angle BAD and BAD is congruent to angle CAD, then we have that angle FEH is less than angle CAD by proposition 3.21 part B. And since angle CAD is greater than angle FEH and FEH is congruent to BAJ, we can conclude by proposition 3.21 part C that angle CAD is greater than angle BAJ. So then, by definition of greater than, we have that there's a ray AK between ray AD and AK such that BAJ is congruent to angle CAK. Since angle CAJ is congruent to FEH by step 5, and angle FEH is congruent to BAJ, and angle BAJ is congruent to angle CAK, it follows that angle CAJ is congruent to angle CAK by Congruence Axiom 5. So in step 9, we showed that angle CAJ is congruent to angle CAK, but this produces a contradiction because CAD is greater than one angle and less than the other angle. CAD is greater than angle CAK by definition of angle CAK, and it's less than the congruent angle CAJ. So this contradicts proposition 3.21 part A. And so we can conclude that all right angles are congruent. So we'll end this lecture with a couple of definitions. An angle is acute if it is less than a right angle. An angle is obtuse if it is greater than a right angle. And now that we've finished looking at congruence axioms, we can define a Hilbert plane. A model of our incidence, betweenness, and congruence axioms is called a Hilbert plane. And these models are discussed more in chapter 4.